Greetings everybody and welcome back to another video. It's been way too long yet again since my last video. I don't even know when my last upload was. I've just been way too busy with uni to do all this YouTube stuff on the side. But yeah, at least it's week 12 now and I only have one more assignment to do and I just kind of want a break. So we're going to take a look at a bit of complex analysis today. I haven't touched complex analysis in so long, because I did complex analysis last semester and now I don't really have any reason to do it anymore except to make videos, but it's still fun to do a bit of complex analysis here and there. So we're going to take a look at this integral today. I had this one in my notes ready to go for a while and I forgot to bring my notebook today with like the solution and whatnot. So I'm going to try to do this one off by memory and hopefully, everything goes to plan. So this is a pretty wild looking integral. We have an arctangent and a logarithm and maybe you've seen arctangent in complex analysis before. It has like branch cuts and everything. So you might think, well, we're probably going to be messing around with plenty of branch cuts today with this sort of integral because we have a logarithm as well. It turns out we won't be touching a single branch cut, which is pretty cool, pretty surprising as well. So what can we do with this first of all? Well, I want to kind of rewrite that arctangent a little bit. There's a nice way you can express this arctangent using a logarithm, which I don't have at the top of my head. So I'm going to cheat a little bit and look at this stack exchange article. So we have negative 1 to 1, we have 1 over 1 plus x, and then the formula for arctangent, I'm going to put the 1 over 2i at the front. So arctangent, you can write it as 1 divided by 2i, and then you have the logarithm of just some random stuff. So it goes like a 1 plus ix on the top, and then divided by 1 minus ix. Okay, and we have this logarithm guy over here as well, so you might as well do something with that. So we have a logarithm. I'm going to separate this out because notice we have 1 plus x squared, and we have like 1 plus ix, 1 minus ix, so you might think, well, might as well do some kind of difference of perfect squares over here. So we're going to do exactly that. We're going to rewrite this as 1 plus I times x, and then we have 1 minus ix. So if you multiply this out, that's going to give you 1 minus I squared x squared, which is 1 plus x squared. So this is all divided by 2, and that should be everything for that logarithm. Okay, so now we're going to start separating the logarithms out a little bit because we just have a bunch of factors in the logarithms. Now notice with the second logarithm over here, we have a 2 and we have 2 factors. We kind of want some nice symmetry to happen between these 2 factors. I'm going to rewrite this 2 as a square root of 2 times the square root of 2. So we can kind of split them up nice and symmetrically, I guess. And because we have like something over root 2, like we have 1 plus ix over root 2, 1 minus ix over root 2, we might as well get some root 2 action happening in this first logarithm as well. So what I'm going to do is I'm going to divide the top and the bottom inside of that, in this fraction, by the square root of 2. So we have a root 2, and this guy over here is also divided by root 2. Okay, lovely. So now what do we have? We have 1 over 2i, integral from negative 1 to 1. We have the 1 plus ix still chilling out there. And then I'm going to use the logarithm laws for this first one and the second one as well, just to split everything up nicely. So what will this first guy become? It's going to become the logarithm of, we have 1 plus ix over 2. And then because we have division over here, we're going to have a subtraction of logarithms. So this is logarithm of 1 minus I times x divided by the square root of 2. Okay, and for the second logarithm over here, you might realize we're pretty much going to end up with the exact same thing, except there's going to be a positive sign over here. So we're going to basically, repeat this factor, this whole entire factor over here, but we're going to change this negative into a positive. And you might realize something, instead of having to write out that whole thing again, well, we're just going to have something plus something over here, where these are the somethings respectively. That's just difference of perfect squares yet again. So actually, this just becomes this squared minus this thing squared. Hopefully that's clear. We have a minus b, then times a plus b, so that's just a squared minus b squared. Nice and simple. Now, we have gotten ourselves 2 logarithm squares. Might be a bit tricky to work with that, but it's actually not too bad because we have some conjugates happening on the inside of the logarithm there. So we have a 1 plus ix and then 1 minus ix, but we might as well write this guy over here as 1 plus ix but with a conjugate, because remember, x is a real number, it's varying on the interval negative 1 to 1. So this is just 1 plus ix, and then we can put a little nice conjugate up over there. Actually, we might as well do it for the whole thing, because 1's a real number. Okay, so why do I decide to write it like that? It's because now I can use some nice conjugate properties and how it interacts with, polynomials and logarithms and whatnot. So let's do a little bit of an aside over here. If you take a look at the logarithm of some complex number, let's say z over here, with the conjugates on top, this is actually equal to the logarithm of the complex number with a conjugate. But you have to be careful, this only works if you're on the principal branch, which is from negative pi all the way up to pi. So the reason why this works over here is because, well, let's say z, you decompose it as r e to the I theta. So this is just the logarithm of the radius, and then you have a plus I times logarithm of e to the I theta using log laws, but this is just plus I theta over here. Okay, but because we have a conjugate on top of your z, you actually pick up a negative angle. So this actually becomes negative I theta, but then this is basically just this guy over here, because this is, we can write it like this, logarithm of r, and then plus I times theta, and then everything with a conjugate on top, and that's equal to that guy up over there. So you can bring the conjugate inside the logarithm, outside the logarithm, assuming we're on the principal branch, which we'll just assume we're on. Okay, so in particular, we can bring this conjugate outside of the logarithm, and we also have this squared on the very outside of the logarithm as well, and that we can also pull out. So z bar squared is the same as z squared bar, I guess. So you can bring this whole entire conjugate, extend it all the way out to the outside of the whole entire logarithm, which is really quite nice, because now you'll notice we have something minus the same something with a conjugate on top. And, well, maybe you know this result. If you have something like this, you can rewrite it as something to do with the imaginary part, I believe. Let's actually try it out over here. If we have a complex number z, and you take a look at z minus z conjugates, like we have over here, well, we can rewrite this as, well, this is a plus bi, let's say, and then we have a minus a, and then z conjugate is a minus bi. So this is a minus ib over here. Oh, I don't know why I wrote it in the reverse order. And this is a minus a, that's 0. And then you have bi minus negative bi, that's just 2bi. So 2bi over here. So really what you're left with is just I times 2 times the imaginary part of z. So this is 2i im z. Okay, so this is really quite nice over here. So we can insert this into our integral, and we have a 2i. You might notice out over here, that's going to cancel with that 1 over 2i at the very front, which is pretty cool. So let's do a bunch of substitutions and cancellations. So this is equal to now, the 2i out here is gone because we have a 2i there, and we have the integral from negative 1 to 1, 1 over 1 plus x. And then what do we have? We have, well, we just have imaginary part, I believe, yes, imaginary part of the logarithm squared of 1 plus I times x, and this is divided by the square root of 2. Okay, so we've reduced the integral quite nicely. Now I want to take a little bit of a precaution with the integrands, I guess, because what I wanted to do now is I want to move this imaginary part operator outside of the integral. But the problem in doing so is that on the inside over here, we have a 1 plus x. That means we're going to have a singularity at negative 1. I believe it would have been removable from the very start, because if you have x equals negative 1, then this is, you get some kind of cancellation with the L'Hopital's rule or something, I believe. I'm not too sure. But what I'm going to do now is, instead of going from negative 1, because negative 1, there's going to be a singularity there, we're going to start at negative 1 plus some kinds of epsilons, and we're going to take the limits as epsilon approaches 0. So I'm going to stick the limits right out over here. So this is equal to limits as epsilon approaches 0 of this integral, just so we stay away from the singularity, and then we can do some residue theorem stuff later on. Okay, so let's move the imaginary part operator outside of the integral, and then we should be able to get some nice integral we can work with. Okay, so now we have this fairly nice integral, I guess, and what can we do with this? Well, we have a bunch of junk inside of this logarithm squared over here, so we might as well just do some kind of substitution. The downside with that is we're going to turn this path that's on the real line at the moment into some imaginary path, because we have some ix happening in here, but that's okay, because that's why we're doing contour integration. So let's do our substitution now. I'll do it, we'll just do all of our side working out on the side here, I guess. So substitution. we're going to let z be equal to precisely the thing inside of the logarithm. So that's going to be equal to 1 plus I times x divided by root 2. And if we want to do the substitution, we better know what the differential is. So let's try to calculate dz. So that's not too tricky to calculate, hopefully, because it's just going to be I divided by root 2 times dx. So we have I divided by square root of 2 times dx. That means if we want to sub dx in, that means that, dx is just going to be equal to, root 2 divided by I, well, that's the same thing as negative I root 2. And now this chalk is getting too small, so I need to change chalk. They don't put any nice new chalk in this room anymore for some reason. Probably because they found out I was recording in here and they don't want to, fund my chalk usage or something. Anyways, so we have our dx figured out. And we probably also need this x down here as well. So let's figure out what x is. We just need to rearrange this, substitution, which isn't too bad. So that's going to be square root of 2 times z, and that's equal to 1 plus I times x. Okay, we can bring the negative 1 over, so this is, root 2z minus 1 is equal to this ix over here. Okay, and then we just have to isolate x, which isn't too bad to do. So x is equal to, we're just going to multiply everything through by negative I, because, negative I times I is 1. So this is equal to, we have, let's do this 1 first maybe. So this is going to give us an I believe. And then we have a minus I, square root of 2, and then times a z. Okay, so we have everything we need now. Maybe we need to figure out what the bounds are going to become, but we'll figure that out later. So now, what do we have? We have the limits as epsilon approaches 0 of this imaginary part of boy over here, and then we have some kinds of integral. I'm just going to leave it as that at the moment. Then we have the logarithm squared, and this whole thing, we substituted that for z, and now this is divided by, we have 1 plus x, but 1 plus x, let's see, let's figure that out actually. So 1 plus x is going to be equal to 1 plus I, and then minus I square root of 2 and z. And now if I remember correctly, we want to rewrite this 1 plus I in a bit of a nicer way, because you might notice 1 plus I on the, I think is it the Argand's diagram or something, I don't know, the complex plane, it's sitting right over here, and you can rewrite 1 plus I, so this vector or whatever over here, as square root of 2 e to the I pi on 4. Okay, and I'm actually going to define this e to the I pi on 4 as being some kind of omega. I'm just following, the solution on Stack Exchange pretty much. So they just replaced that with an omega, just so we can save a bit of chalk today as well, I guess. So we have the log squared of that guy. So 1 plus x now is equal to square root of 2 omega minus I square root of 2z. So let's plug that in over here. We have the square root of 2. Let's factor out the square root of 2. Why not? And then we're left with an omega minus I times z. Okay, and then we have the dx to worry about as well. So dx is equal to, let's do that. That's negative I square root of 2, and then a dz. And something quite nice happens. We have root 2 and root 2. Those will cancel. Let's also multiply this negative I into this thing over here. So this is limit as epsilon approaches 0, imaginary boy, integral. And then we have the logarithm squared of z divided by, now negative is going to jump into here, so that's going to turn it into, and also I is going to cancel. Let's grab some yellow chalk. Is there even yellow chalk left? Oh, yes, there is. Okay, so the I will cancel with this I, so will the negative will cancel over here. So we're just going to be left with a nice z, and then now we have to take omega and divide it by a negative, so that's going to be some kind of negative omega, and then we have to divide it by an I. But dividing by I, well, if you take a look at the picture over here, dividing by I is the same thing as multiplying by negative I, so you're just going to rotate, what is that, pi on 2 radians clockwise, so you're actually going to end up over here. So your angle is going to become negative I pi on 4 now pretty much, but you can just rewrite this as omega conjugate, which is quite nice. And then we have a dz. So this should be right. So we have the log squared, that's sorted, and then we just did some cancellations with this part with this denominator. Okay. And we also need to figure out what on earth the bounds are. We should probably get a handle on that so we know what we're integrating. So because we're just going on a straight line over here from negative 1 plus epsilon to 1, if we map it over using some kinds of linear substitution, we're just still going to get some line in the complex plane. So it suffices just to know what the start and end points are. So if you take a look at where 1 gets mapped, Well, if we sub it into the substitution, we're going to end up at 1 plus I divided by the square root of 2. But that's just e to the I pi in 4. So actually, that endpoint over there, that 1, is going to be, let's do yellow chalk now, and that's going to be all the way up over here at, just your omega. Well, that's equal to e to the I pi in 4. Okay, and where's the start point going to be? Well, let's just plug in -1. So -1, that's going to land you at 1 minus I over root 2. But hey, that's just equal to omega conjugates, which is down over here. So omega conjugates, that's equal to e to the minus I pi in 4. Okay, and because this is going to end up being some kind of straight line, and we're starting at -1 plus epsilon, the path of integration is actually going to start slightly above this point over here, and then we're just going to integrate up like so. So this is our path of integration. I'm going to call that, let's call it psi. This is our path over here, so we're integrating psi and over psi. Okay, now the next question is, how on earth do we even get a nice value? How do we evaluate this integral? We can't just parameterize, otherwise we just reduce it back to what we had before. What we're going to do actually, you might notice that this is on a nice, well, they're actually points in the unit circle, so maybe we can make use of that somehow. So let's draw the unit circle over here. It's probably going to look something like that. That's, decent circle, I guess. So what we can do, actually, is maybe we can, instead of integrating on a line, it's much better to integrate on a circle. It's just nicer to parameterize. So what we can do is what we want to start down here ends up over here. So why not take a bit of a detour down onto the circle using some kind of arc? So we're going to, take some nice curvy arc down to the circle. I'll call that gamma. And then we can go from down here, and we can traverse along the unit circle all the way up to this point. And I'm going to call that other part over here, I'm going to call it gamma. Okay, so this is our plan, the integral over psi at the moment. We can, using path independence because there's no other singularities in that integrand besides 0 and omega, or omega conjugate, which is down here. Those are the only two singularities. We can deform this path, and we can break it psi up into little gamma and big gamma. So let's do that. I think I might be able to fit this whole solution on one blackboard, which is quite nice. So let's move over to here now. So maybe I should index things by epsilon. Doesn't really matter, but I'll just put a little epsilon down here. Can you guys even see that? Yeah. And then I'll put some, I'll call this gamma epsilon and little gamma epsilon down here as well. Okay, we're just going to evaluate each of those integrals, take limits as epsilon approaches 0, and also take the imaginary part eventually, and then that should be the result for our original integral I, which is quite nice. Okay, let's take a look at the integral over, we'll do big gamma epsilon first. And we might as well call this function in here, we'll just call that function f of z, why not? Or we don't even need to call it anything, we'll just write it down, what am I doing? So we have the log squared of z divided by, we have z minus omega conjugate. And then this is dz. So let's just do a parameterization now because we're on a circle. So what's z going to be equal to? Z is going to be equal to, we're on the unit circle, so it's just going to be e to the I theta. So let's do the parameterization here. So gamma epsilon z is equal to e to the I theta. And theta is going to range from, it's going to go from, we're going to take the limits eventually, so we might as well just say it's going to go from -π/4 up to π/4 for the angle. So this is equal to the integral from -π/4 all the way up to π/4. We have the logarithm squared of, what's z? It's e to the I theta. So this is e to the I theta. And this is divided by, we have z, which is e to the I theta, minus omega conjugate, which is, let's write this as e to the I π/4. -I π/4 actually. And then what is dz going to be? Well, just differentiate this guy using chain rule. That's I times e to the I theta. I'll just write it down here. So we have an extra times I e to the I theta d theta. Okay, and we can cancel some things with the denominator and that factor at the ends there. So this is integral from -π/4 to π/4. And then notice log squared of e to the I theta. Log and e are going to cancel, leaving us with this I theta squared. But I theta squared, that's just negative times theta squared. So this is a negative theta squared out over here. And divided by, notice we have an I we can probably pull out to the front, which is quite nice. And then e to the I theta, e to the I theta, that's going to cancel, leaving us with a 1. And then minus, we have, e to the minus I π/4. And then we're going to cancel with this e to the I theta, so this is actually I theta pi and 4 minus a theta in there. D theta. Okay, and now we need to take, we need to take care of that imaginary part operator as well. I forgot to put that in. So this is an imaginary boy, and then another imaginary boy. And then we're going to take the imaginary boy of this whole thing over here, so an im with this whole thing. Now, we have imaginary part of, something in here. So imaginary part of I times complex number. There's actually a nice way to rewrite this. Let's put that somewhere. Let's squeeze it in this corner up over here. If you take the imaginary part of I times a complex number, I believe that's like a real part of something. I don't know. Let's find out. So this is equal to the imaginary part. Now, if you write z as a plus bi, this is going to give you ai, and then because we had the plus bi, and then we're multiplying by this I over here, that's just going to be minus b, so this guy over here. So this turns out to be just the real part of exactly z, because imaginary part of ai minus b is precisely just a, but that's, the real part of z. This doesn't work the other way, I believe. If you take the real part of I times z, I believe it should be negative imaginary part of z. But we have imaginary part of I times some complex number probably. So this is just going to reduce to the real part of, just this integral. And we could also move the real part operator inside of the integral as well. So let's do that. This is equal to, this I is gone, so we have integral from negative pi and 4 up to pi and 4. We have the real part. We can pull this negative theta squared out as well, because theta is a real number, it's a parameter, and then we have the real part of 1 over 1 minus e to the minus I pi and 4 minus theta. And now we're going to use some nice fact about this sort of expression over here. If we have the real part of 1 over 1, I think it's, minus e to the I theta or something like that. That's going to be equal to, what was it? I think it was 2. Or was it 1/2? I think it's 1/2 actually. This is something you can try. Homework, I guess. So if we ever have something of the form real part of 1 minus e to the I times t for, t, any real number, I guess, this is always equal to 1/2. Doesn't matter what value of t. The way you prove that is you just use Euler's formula and a little bit of completing the square, whatever it's called, just to get rid of the imaginary thing on the denominator, and just expand a few things here and there. And you should be able to get that result, no problem. So let's just use that result over there. So this is integral negative pi on 4 to pi on 4. So this just becomes negative theta squared on 2 times d theta. Okay, and that's pretty easy to evaluate. We can also, get rid of this 2 over here and start from 0 because theta squared is a symmetric guy. We'll get rid of this 2. So we're just integrating theta squared pretty much. And this just leaves us with a negative. We get theta cubed on 3, but we just plug in pi and 4. So that's going to be 1/3, and then we have a pi and 4. This is raised to the 3, and this is equal to, negative 1/3 pi cubed on 64. So that's quite nice there. Okay, so we've got the integral of, big gamma epsilon out of the way, and we've also taken the limit as well. In this step. And now let's take a look at the integral over little gamma epsilon. And so this one's quite nice over here because you might notice omega conjugate, that's a simple pole. And because we're doing a little small arc around this pole over here, and we're taking limit as epsilon approaches 0, it turns out this is just precisely equal to some factor times the residue. And it turns out that factor is precisely this angle we're making. Because usually if you do a full circle around this, it's going to be 2 pi I times the residue. But that's if you do the full circle, it's 2 pi radians. But now if you just do this little angle over here, the value of this path integral is just going to be I times the angle times the residue, which is quite nice. That's something quite simple to calculate. So the integral over gamma epsilon in the limits as epsilon approaches 0 is equal to I times the angle, which is pi and 4. If you stare at this picture for long enough, you can convince yourself this angle down here is pi and 4. And then we have the residue at z is equal to, omega bar. That's the simple pole there. And we'll just use the residue formula for simple poles, which is equal to, we have this I times pi and 4 hanging out here still. It's the limits as z approaches omega bar. And then you do z minus the pole, times the function. But notice the function on the denominator, it is z minus the pole. So it's just going to cancel, leaving us with the logarithm squared of z, okay? And that's just something we just got to plug in and compute. So this is I pi and 4. We have the logarithm squared of e to the minus I pi and 4, okay? But now log and e are going to cancel, and we're just going to be left with minus I pi and 4, but squared. Okay, so this is I times pi on 4, and then we have times negative I times pi and 4, but this guy over here is squared. Okay, but minus I squared, that's exactly equal to 1. So this is just going to give us I times pi cubed on 64. Lovely. Okay, and remember we need to take the imaginary part of that stuff out over there. So yeah, if you take the imaginary part of this thing, that's, yeah, pretty obvious. It's just pi on 64. Okay, so we're pretty much done here because we've got the integral over gamma and little gamma, big gamma and little gamma sorted. So let's just combine all the results over here on this line. So we found this was the limits of the imaginary part of this integral, psi, which was gamma, big gamma plus little gamma, and well, we have the results right over there. So this is simply equal to, little gamma was pi cubed on 64. So we have this guy over here, and big gamma was negative a third pi cubed on 64. So we have minus 1/3 pi cubed on 64. And what is this? This is just 2/3 pi cubed on 64. And let's see if we can simplify this. 2 and 64, that's, what is that? 32? Yeah, 32. So this is 1/3 pi cubed on 32. And 3 times 32 looks like that's just 96. And that is the final result for today's integral, pi cubed over 96. Whoa! Okay, so that's, yeah, the final result of today's integral. Quite a nice result. So yeah, that's all for today's integral. I don't know when I'm going to be back filming my next video, probably after exams, because yeah, I really don't have much time after this one. I just felt like doing a video today. So yeah, hopefully you guys enjoyed this video. If you have integral suggestions or whatever stuff you want me to do, feel free to leave it in the comments below. And yeah, hopefully I'll get to it after my exams. Yeah, so that's all for today. Hope you guys have a wonderful day. And I'm going to eat this banana now because I'm getting quite hungry. Yeah, so hope you guys have a wonderful day. Enjoy the rest of your day, and I'll enjoy this banana. Bye-bye. I just realized I probably shouldn't be eating, otherwise I'll probably get chalk dust in my banana. I don't know if chalk is good for you or not.